Hey guys, just in case those other two problems that we did weren't exciting and awesome and fun enough, we've got another problem here that combines the Newton's laws that we've been learning about in this chapter with all the kinematic stuff from chapter 2, I think. So, it's twice the fun. Hope you enjoy. Here's my dad.
Well, thanks again, Hannah, for that stirring introduction. Indeed, we will do a problem using Newton's laws to find information that we can then use to solve a kinematics problem. So, here's the problem. A box, mass 35 kilograms, is shoved across the floor by a force F, which is 520 newtons, but the force is exerted downward at an angle of 30 degrees below the horizontal. The coefficient of kinetic friction between the floor and the box is 0.45. So first we want to find the acceleration of the box, and secondly, if the box starts from rest, how long does it take to move 5.5 meters? Well, we're going to start as usual by drawing a free body diagram for the mass, which is the box. So here it is, and we know what some of the forces are that are acting on it. There is a normal force because it's in contact with the floor. There is, of course, the force that's being used to push on it, which is F, and the number is given for that. There's the weight, or the gravitational force, downward, F sub g. And of course, because it's moving across the floor, there's some friction. And it's sliding friction or kinetic friction, F sub k. And once again, remember that when you've got a frictional force for sliding friction, F sub k is equal to mu sub k times the normal force. And that will come into play in a few minutes. All right, let's also put into the sketch the angle with the horizontal, which we're given the numerical value of 30 degrees for. But I'm just going to put theta in, because one of the things that I think is very important is to solve problems using symbols in the solution and only plug numbers in when you're ready to solve for your final answer. Now this force F, downward at an angle of 30 degrees, then can be broken down into x and y components. But first, let's draw in our coordinate system, which is pretty obvious here. X horizontal, y vertical. And so we'll take that force F and draw a right triangle so that we can see it's got an x component and it's got a y component. And we can figure out what those are using a little bit of trigonometry, because the cosine of theta is F sub x over F, which means that F sub x is F cosine theta. And using very similar work, the sine of theta is the opposite side, or the F sub y, over the net force F, so that the y component of that force is F sine theta. Okay, we're ready to go. Now, to find the acceleration, this is the work involved in part A. We first write down Newton's second law for the x and y directions. So we add up all the forces along the x direction, and when we do that, on the right hand side we're going to get the mass times the acceleration along the x direction. Then we'll do the same thing for the y direction. The sum of all the forces in the y direction has to equal the mass times the y component of its acceleration. So, x direction first. In the x direction we've got the x component of the force F, and I've called it F sub x, and we'll substitute for it in a minute because we know it's F cosine theta. We've also got, pulling to the left, the frictional force, the sliding friction force. So F minus Fk is max. So F sub x, we already know that's F cosine theta. F sub k, what I wrote down earlier, was mu sub k times the normal force, and on the right, max. Now we're trying to find the acceleration, which is the acceleration in the x direction. So in this equation, we've got that on the right-hand side. We know the mass, we know the coefficient of friction, we know the angle, we know F, but we don't know the normal force. So we can't solve the problem just yet, which reminds us to go over to the equation for Newton's second law in the y direction. So in the y direction, we've got, in the positive direction, the normal force, F sub n. We've got, in the negative direction, the weight or the gravitational force, and we've also got the y component of the force F, this being exerted to push the box. So on the right-hand side, a little thought will remind us that the box is only moving in the x direction. It's not moving in the y direction, so the y component of acceleration is 0. So let's use this to solve for the normal force. F sub n equals Fg plus Fy. Of course, Fg is simply the weight, or mg. Fy we have written down as F sine theta. Alright, so this is F sub n, and now we're going to take this expression for F sub n and plug it into the equation that came from the sum of the forces in the x direction. So rewriting this, F cosine theta minus mu sub k times this entire term, mg plus F sine theta, equals mass times a sub x. Well, a sub x is what we're trying to find. So let's divide through by m, and if I do that and turn the equation around, we get a sub x is equal to, in the numerator, F cosine theta, and I'll distribute through the coefficient of friction, minus mu sub k mg minus mu sub k F sine theta, all divided by the mass. And now to find a sub x, we are ready to throw in the numbers, because all of the terms on the right-hand side are terms that we know. So I'm going to write the numbers in carefully and then give the numerical value for the acceleration, and we'll be finished with part A. So remember that when you plug numbers in, you should always plug in the units as well, and make sure that the units work out consistently. So the force F is 520 newtons. We've got the cosine of 30 degrees minus mu sub k is 0.45. mg, well, we've got mass of 35 kilograms. 35 kilograms times, of course, 9.8 meters per second squared. And then we've got one more term in the numerator, minus 0.45, once again, times the force F, 520 newtons, times the sine of 30 degrees. So all of that's in the numerator. The denominator then just has the mass, which is the 35 kilograms. And each term in the numerator, if you work the units out, has units of newtons. Newtons divided by kilograms gives us meters per second squared, which is appropriate for an acceleration. And numerically, the acceleration that we get is 5.1 meters per second squared. So that's the answer to part A. And here's where we see the connection between information we get from Newton's laws and information that is needed in kinematics, because part B says to find how long it takes for the box to move 5.5 meters if it starts from rest. And that turns out to be a pretty easy problem. So we know, just make a list of what we know. If it starts from rest, then v0x is equal to 0. We know delta x, since it moves 5.5 meters, that's delta x, 5.50 meters. We also know the acceleration, a sub x, and we're trying to find the time, how long it takes. So the equation that we want, after a little thought with kinematics, is this one. delta x equals v0 xt plus 1/2 ax t squared. And what makes this nice is we know the initial velocity in the x direction is 0. So that first term on the right hand side goes to 0. We know then that delta x is 1/2 ax t squared. So solving this for t, we can first solve it for t squared and then take the square root. And when we do all that, we'll get the square root of twice delta x over a sub x. So here, to plug all the numbers in, we get twice 5.50 meters per second squared divided by 5.1 meters. Oh, sorry, in the numerator, that shouldn't be meters per second squared. That should just be meters because it was delta x. So I'll scratch that out and make it meters. The denominator really has the acceleration, so it is meters per second squared. And that means underneath the square root we have meters over meters per second squared, which means we get seconds squared. The square root of seconds squared is just seconds. And sure enough, the answer then has the right units, and the numerical value is 1.5 seconds. Seems like a short time, but I guess that's quite a force that was used to accelerate the box. So, just to recap, we used Newton's second law and information about the forces that was provided to figure out the acceleration. And with the acceleration and review of our knowledge of kinematics, we found out the time it would take to reach a distance 5.5 meters. Hope that was helpful. It might be like other homework problems that you have to solve, so go for it.